Oh, good. Okay, we're live. Hey, so I'm Robert Seacord. I'm the standardization lead at Woven by Toyota. I'm the convener of the C committee. I've been here before. I've been joking if I die this upcoming year, they'll probably dig up my body and pump some zombie juice in and make me present again. So I picked this topic, I thought by accident, on composite array types in C. But as I've sat through the 2 days, people actually are talking about type safety and strong typing, and this talk will be is sort of along those lines. So again, yeah, that's me. I think I said all those things. So I'm talking mostly about arrays in C, which is really outside my comfort zone. Normally I talk about integers in C, as my boss likes to joke about. But yeah, I gave a 2-day workshop here called Secure Coding in C and C++, because if I hadn't lied to people and I was honest and called it, 2 days of integers, probably no one at all would have signed up. But once you're in it, it's not as bad. Very simple introduction stuff that hopefully will be a surprise to no one here. Arrays are contiguously allocated sequences of objects, all have the same element type. They're characterized by their element type and the number of elements in the array. So for example, this would be in C or C++, an array of integers with 11 elements of type int. And this talk is really about C. It is not a C++ talk. I don't think the concepts I'm discussing here are familiar to C++. So C++ is more serious about typing. C is a little more lenient, a little more. I've been using the phrase in my head for the last 2 days. User friendly, right? So yeah, we're C is all about getting things to compile, so you can get to the real job of debugging your code. And here we've just an array of 17 elements of pointer to float. So these are things that all of us know. There's a square brackets is used as a subscript operator to identify an element of an array. So here's a very contrived example that has an array of 10 elements with a bound of 11. Simply loops, adding 1 to 0, which is actually one of the defined operations you could perform on strings. Generally not recommended, but it's okay here. And then we just create a no-terminated loop. So this is where C and C++ start to diverge. C has the concept of types that aren't exactly the same, but are compatible. They get along all right. Like in a dark room, they sort of seem to be the same. So two types are compatible if they're exactly the same. That's pretty simple. There are additional rules, and the rules are distributed throughout the standard, but most of these sections actually have no rules. So there are a limited sort of set of compatible types. And of course, two types don't have to be exactly the same to be considered compatible. But by default, they are incompatible. They're not compatible. So there has to be a rule explicitly saying that they are, otherwise they're not. So array types, and again, this talk is mostly about array types, are compatible if they have compatible element types. That's the first prerequisite. But then there's this interesting sort of phrase here where if they have size specifiers, and only if they have size specifiers, then there's a little bit more to the rule. So if the size specifiers are present in both arrays, and those size specifiers are integer constant expressions, then both size specifiers must have the same constant value to be compatible. So we also have in C the idea of a composite type, and I would say, I started programming C in 1985. Not my first language. My first language was probably Fortran or Watt5S. But as of 6 months ago, I probably had really no idea what composite types were. But people kept talking about them to the point where I finally thought I need to understand this. And also I got nerd sniped into a paper. So there's the concept also composite types, which can be constructed from compatible types. So if both are the same, if you have two compatible types that are same, that's also the composite type of the two. Otherwise, this type that's compatible with both, but quite possibly is neither, right? So composite types are used two places in the standard. So they're used for conditional operators. So, a hint here is if you don't want to understand composite types, one thing you can do is never use conditional operators. That'll eliminate, half the use cases of this. So conditional operator uses composite types. If both operands have structure union type, the result is the composite type. If they're pointers to the same or differently qualified versions of compatible types, the result type is pointer to an appropriately qualified version of composite type. Appropriate is one of those words I always highlight when I see it because it's a standardization term, which means like it's almost undefined, right? Like there's what is appropriate, we're not telling you. So here again, just the example of the conditional operator, the tertiary operator maybe as you know it. So the second place composite types play in C languages in prototypes. So, and this is maybe more common. People like conditional operators, not everyone uses them. So a declaration of an identifier for an object that has a file scope without an initializer and without storage class extern or thread local is referred to as a tentative definition. So here we've got just, in file scope, you could say int global variable. So that's a tentative definition with external linkage. Or we could say static int, static global variable. Now we have a tentative definition with internal linkage. So a type with tentative definition is determined. So if the composite type, the composite type with tentative definition is an array of unknown size at the end of a translation unit, that type becomes an array of size 1 of the composite element type. And so that's a bizarre rule. I didn't actually remember that until I reread the slides this morning, that it just basically says, well, we don't really know what the size of this is, so we'll imagine it's 1 and keep going from there. So again, C does kind of, I'm going to reuse the phrase, it's programmer friendly. It's kind of like, if you get in the ballpark with your types, we're going to allow it, right? We don't really go out of our way as Rust does to make sure that you can't write code that doesn't work, right? We want you to do what you feel you need to do, and we're going to trust you that you've done it correctly. And we all know that sometimes that trust has been misplaced. So otherwise, the type is the composite type in the end of the translation unit. So these two mechanisms for forming composite types are different. Why would they be the same? So the conditional operator requires its operands to have compatible types to form a composite type. Prototypes aren't subject to the same set of constraints, and they can overrule other prototypes to create valid composite types out of potentially incompatible types, right? They can just go that extra mile to say that, yeah, okay, I mean, normally these would be incompatible, but we're going to pretend like they're just the same. And so this is viewed as probably more of a defect in the standard than anything else. So with a little bit of luck, someone, ideally beside me, will write a paper to fix this, and otherwise, perhaps it will be me. We'll see. This is not really, again, my comfort zone. I do write the integer papers, though. I write a lot of integer papers. Composite types, again, build on array compatibility, and the issue here is that the compatibility is not really precisely defined. So, again, composite types can be constructed from two types that are compatible. If both have the same type, that's the composite type. Otherwise, its type is compatible with both and satisfies, boatload of conditions. So when we're discussing arrays, an interesting part about arrays is there's quite a number of ways to specify the size of an array. So the first type of an array we can have is an array of known constant length. And so this is probably simplest and most common thing. This is also present in C++, but you can here have an array of one int element. The length expression has to be an integer constant expression, and complete type has a size that's less than or equal to size max. And the index operator takes an expression that's constrained to be an integer type. It doesn't have to be an unsigned integer type. It can be int size t. It could be bool. It could be any integer type, pointer diff t. It can't be a floating point type. That would be a constraint violation. So the size, of course, has to be a positive integer value. You can have some fun with, say, passing a negative size to a VLA, which is a pretty easy exploit to develop. So this is, one of the reasons maybe VLAs are not present in C++, and sort of constantly under attack in C. The history of VLAs was we put them in to C99, and then we took them out of C11, made them optional, and then for C23 we put it halfway back in. So now it's sort of halfway required and halfway optional. But the required part is very, very useful and not particularly dangerous, and the optional part is the part that's a little more prone to misuse. So second, we could have an array of known variable length, and here we just have an expression that's evaluated at runtime, right? So it could be n, it could be passed into a function, it could be read from a command line, or input from, I guess, an untrusted, tainted source. N can be evaluated or unevaluated depending on the context. There are situations where length expressions are not evaluated, but the type is needed. In C23, this can lead to undefined behavior in conditional expressions. I qualified that as in C23. Well, in C23 and earlier versions of the standard, what ISO would call obsolete versions of the standard, right? Because they only recognize the one true standard as existing. So in C2Y, we've fixed this. We have an effort underway. We have an undefined behavior study group, and they're going through and mostly just renaming things, so they're not undefined behaviors anymore, but they're reclassifying undefined behaviors frequently as implementation-defined behaviors or constraint violations. In this case, the solution we used was to make these constraint violations, but I'll have more on that in a moment. So the UB, if you have a type which is a variable length array whose size is specified by an unevaluated expression, that creates undefined behavior. So here we have a function that takes a couple pointers and a condition, and we have a conditional expression where, as I mentioned, composite types will be formed to evaluate a conditional expression. And so based on the condition, if the condition's true here, this, let me get my marker, this expression is not evaluated. So this sets up for an undefined behavior. So both types here are used to determine the composite type, but really there is no composite type because there is no type here to compose. So the third way we would specify the size of an array is with a splat between the brackets. So these are arrays of known variable length where the length is unspecified. So these are only used in contexts where the actual type has a specified length by the time it's used. So it's where you don't need to know the type at the location this is used. So it's a placeholder really for the length expression. It's kind of the wild card will match anything with this use of the splat operator. Yep. So again, it can be used in places where you need some sort of placeholder, but the length isn't needed at that point in the code. And finally, we can have an array of just unknown length. So there's just nothing between the braces. So arrays of unknown length can only be used if their length is not needed. This is an incomplete type, so this can't be used in a situation where the length needs to be known. One application of these are in flexible array members, right? So you can have an array at the end of a struct where you basically dynamically allocate the storage for that at runtime, and this is a how do you call this? This is sort of a kludge, is that the right word? It's one of those things that people started doing and became fond of, and then it got sort of retrofitted into the language. And so, theoretically it might be nice to have this anywhere in the struct, but someone had them at the end of the struct, and people sort of over time felt like that was good enough if we just have it at the end. Yeah, I don't know, like today, if this would be necessary. I mean, presumably VLAs could meet this role, but this is the problem I have going off script. Never go off script, because now I don't know, like, can you have a VLA in an array? Because how do you calculate the size of the structure now? So, yeah, let's just pretend maybe we need this. So a type has a known constant size if it's complete and not a variable length array. Again, for example, int array 5. Known constant size, definitely not a VLA. An array whose length is an integer constant expression, but whose elements do not have a constant size, are also considered variable length arrays. So here, this might not look like a VLA, but it is a VLA. So the problem, okay, so here we've got an unsigned int size, and a type def to say we want to declare a VLA of this size. So this is going to give us a VLA, but now we're going to have an array with a constant integer size of 5, right? So this is a constant length array, but it's an array of variable length types, right? In this case, a variable length array. And so the size of this entire structure is unknown. And for that reason, the whole structure is considered a variable length array, even though it's sized with an integer constant, right? So that's subtle distinction, which not necessarily readily apparent. So what we've done for C2Y is we've changed the composite type rules in a way that does alter the semantics of the language, to allow a variable length array whose size is specified by an unevaluated expression to have a composite type of a VLA of a specified length. So the UB arises from the unevaluated expressions in the conditional operator, and the UB forming composite types in C2Y has been eliminated by the use of constraints. So we just have now constraints which prevent this and require some sort of compile time diagnostic, either a warning or a fatal error. And this is the paper that was adopted, if you like to read those sort of things. So if we have a type that's an array of known constant length, the composite type is an array of that length. That's quite simple. So here we've got an array of 3 elements of type double, and here we've got an array of unknown length. So the composite type here is the array of known constant length of length 3. And, this is great as long as this is actually an array of 3. Right? If it's an array of 10, it's probably okay. If it's an array of 1 or 2, then, that's a dicier proposition. So the composite type of an array with known constant size, an array with unknown constant size, is always the constant size, because they're trying to lock things down somewhat. So this can lead to UB when the known constant size isn't checked, because really the type system pretty much will give up and trust whatever you tell it is the case. It'll just sort of go along with it and say, sure, let's assume that the other array here is the same size. So in that case, if they are different sizes, we'll have a composite type, but that composite type won't accurately describe the actual object. So here's an example of this type of UB. We have here an array of 10 elements. So this is known constant size. That's obvious. This is trivial to see. But here we've got another array which we initialize using the return value from a function that returns an int, and this function is declared, say, in a different translation unit. So there's no way to really confirm, what value this is returning, and so this will be a VLA, right? Because the size of the array is runtime determined, and so we're going to declare an array of 10 elements, and based on n, which is passed into this function, I could have also made this a Boolean, I guess. We're going to decide if this is either A1 or A2. And so from a perspective of what's statically verifiable here, we know A1 is 10. We know that this new object we're defining is an array of 10 integers. But for this A2 array, we really don't know what size this is. And so the compiler basically just sort of goes along with the idea that this is an array of size 10. So again, this is not Rust style types. This is not C++ style types. This is C being very open-minded about what, in fact, you might have here. So the UB present in this expression cannot be detected by the compiler, right? We have no idea. We're just going to kind of trust that this is going to return the right size. So what happens is, after this initialization, we now have this trustworthy, fully static type which may be entirely wrong, right? It might not be an array of 10 elements, could be an array of 2 elements or 100 elements or what have you. So we can then take, well here, we're just taking the VLA type again and converting it to a constant size array type in order to be used in this function. Or we could do the same expression here and then take the type of it, right? And so the compiler here is once again going to just kind of guess that we're talking about an array of 10 ints. And so APT2 now will be given a static type of array of 10 int. And we know that, well, we don't really know what 10 is returning, but if it's a number other than 10, then that might not be the case. So we have, I thought we had more than one static assert here, but so this static assert, oh, I'm thinking ahead, sorry. So this static assert where we say that the size of this array is 10 will not detect the case where the array is not 10, right? So the static assert will pass here. So this is the consequence of this UB, and it's, again, it's just a pretty weak type system, right? That's expecting you to get it right, get your code right. So if we have one type which is a variable length array with a specified size, so the size is given as n or something like this, some runtime evaluated value, the composite type is going to be the length of that array. So if we have again two types where one type is a variable length array of known size. So the size is this runtime evaluated value size, and here we've got an array of unknown size. Again, the resulting type will be the variable length array of known size. So the composite type of two VLAs with different known lengths is UB because the types are not compatible enough to form a composite type. So it's nice to know in a way that there is a limit to what C will allow. And here again, the type system is likely to just discard this information because there's no real way it can use the information to validate anything, so there's no need typically to keep it around. So the standard does say that if two array types are used in a context that requires them to be compatible, if the two size specifiers evaluate to unequal values, you have, again, undefined behavior. So here we've got both arrays now, A1 and A2, are variable length arrays. And here I've kind of expanded so you can see what size they actually are. But again, you could think of this as being in a different translation unit. So this information might not be available to, at compile time of this function f. And so here again, well, you can see that it's really not 10 in either case, right? It's 8 and 7. So they're not 10. They're different sizes, and the compiler doesn't know Spanish, so Diez doesn't mean anything. It's just an identifier. 10 is the same. It's just an identifier. It doesn't mean anything. But here, we're again statically assigning it. So we will have UB if the two specifiers evaluate to unequal sizes, but that cannot be detected at compile time. So again, we'll form a composite VLA type, convert it to a constant sized array type. This will get converted to a pointer to 10 elements to use in this function. We'll again here, using the type of, do the same thing. We'll end up creating an array I stopped halfway through that because I didn't believe what I was about to say. There's just no even hint here what the type is, right? So really the compiler has just no idea what the size of this is. And because we've had the UB in this expression, we now ask, is the size of this, this new object equal to the size of A1? And the compiler says, yeah, sure. And then we say, well, is it equal to the size of A2? And it fails. And so, both these assertions are being compared to the same composite type. And so the fact that one passes and the other fails is just a clear indication that you have UB in this code and things have gone array. I didn't plan that one. Okay, so if we have a type, it's a variable length array of unspecified length. The composite type is a variable length array of unspecified size. So again, if we have unspecified length here and unspecified length here, we wind up with this this formulation. Basically, we don't know the size. Here, it's quite simple. I mean, these are exactly the same. So if we don't know the array size in either case, we just end up with a composite type where we don't know the size. So the summary of this, and again, this is the C23 behavior because we've taken steps to eliminate the UB in some cases and in other cases to give you a defined result. And the defined result, I guess that's always an improvement, right? Again, but the defined result hopefully is correct. So in C23, so we have the, just a matrix here. So if we have, an array of known constant length, and we have another array of even unknown length, then we'll get an array of known constant length. But the problematic issues are here with unevaluated expressions. If one of the array elements has known constant length, the other's unevaluated, that's a well-known answer. The composite type has a known constant length. But if one of the arrays is a VLA of specified length, of unspecified length, or unevaluated, in all three cases, in C23 you have UB. So I'm kind of jumping a bit here, but in C23, when you have an array whose size is unevaluated, that's going to now become a constraint violation. And for the other two cases, you're going to get a kind of a known size. So it's either going to be a VLA of specified length or unspecified length, depending on the case in that matrix. So the summary here, it kind of starts with this first bullet, which is everything in this presentation is suspect. I mean, if you find yourself in this area where you're combining arrays in, there's two circumstances comes up, right? One is conditional operators. So if you don't want to ever think about this, don't use conditional operators. You've eliminated half the use cases. The other use case is just when you have multiple declarations of this, and they're what's the phrase I used at the beginning of this slide talk, so I don't have to go back and look again, where the types are not set yet. What's that called? You're gonna make me look. Do you ever feel like you've made a mistake? Tentative definition. So if you have declarations with tentative definitions, and those tentative definitions are slightly different, you're going to have this case where the compiler is going to make a decision for you. And so, again, C is trying to be useful, try to be helpful, it's trying to do things for you so that you don't have to find some way to express this idea and sort of be frustrated by the compiler stopping you from realizing your genius in code. So that's the second area, and again, there's no reason you need to do that, right? I mean, so I think this could both the cases where all the situations in this talk arise, I think could be avoided, but especially this second case of the prototype definitions, I think that's quite common. So it's not as easy to eliminate as eliminating the use of conditional expressions, if that's something you want to do. Okay, that talk was in fact as boring as I thought it might be, but are there any questions? Do I have any time left? Can I talk about integers for a while? Okay, thank you very much. Appreciate your time.